Faz parte. Vamos, são duas.
Depois de uma noite de sono num hotel em Lubbock, acordamos relativamente cedo, uma vez que tínhamos algumas trovoadas a sul de nós e alguns dos membros resolveram sair mais cedo do quarto e foram tentar registar essa mesma trovoada. As previsões neste dia apontavam para tempo severo na zona do sudoeste de Oklahoma, pelo que decidimos seguir de Lubbock em direção a Wichita Falls para tentar ver depois onde é que poderiam surgir as células mais intensas. Logo ao início do caminho conseguimos acompanhar algumas células ativas, ainda resultantes da trovoada que tinha passado a sul, muito fotogénicas, mas pelo meio do caminho tivemos que parar para abastecer, pelo que depois acabamos por perder essas mesmas células. Uma olhada incrível. Seguimos, no entanto, caminho em direção a Wichita Falls, como planeado, e começamos a ver algumas supercélulas a querer começar a nascer, digamos assim, na zona a noroeste de Wichita Falls. Tendo depois uma supercélula sobressaído e desenvolveu-se muito mais que as outras, passando a ter aviso de tornado a meio do caminho antes de chegarmos a Wichita Falls. Tivemos que acelerar o passo para tentarmos ainda ir interceptar essa mesma supercélula em relativo excesso de velocidade. Mas conseguimos fazer essa interseção da tal supercélula que até originou um tornado também na zona de Haynesville. Interceptamos essa supercélula na zona de Burke-Burnett, onde tivemos que parar na autoestrada, na berma da autoestrada, e assistimos à passagem da zona do gancho dessa mesma supercélula a norte de nós.
E mais tarde, em Burkburnett, conseguimos entrar numa zona de risco de tornado.
Peraí. Do lado esquerdo. Gosta aí? Temos quase tornado.
Está tornado. Olha ali. Olha ali embaixo. Para aí.
Temos quase tornado. Estou a ver ali, sim.
Se ele baixar ali mesmo. Não é preciso ir para trás, deixa estar, então já está o carro à frente e atrás. Alguma coisa a gente tem que arrancar aí para baixo. Se ele foi ao chão.
Um facto curioso, portanto, enquanto estávamos ali parados a fotografar e a fazer algumas filmagens desse mesmo gancho, alguns transeuntes paravam por ali, alguns cidadãos norte-americanos, e perguntavam-nos, tanto a nós como a alguns outros caçadores de tempestades que por ali também estavam parados, perguntávamos como é que estava a situação, se podiam seguir para a frente, o que é que aconselhávamos. Seguimos depois essa mesma supercélula que estava a mover-se para o nordeste, acompanhamos o seu movimento até chegarmos a uma zona em que tínhamos essa supercélula já a norte de nós, mas tínhamos uma outra supercélula que já vinha também com aviso de tornado a sudoeste da nossa posição. Íamos nessa altura, íamos a seguir também 2 ou 3 carrinhas de uma empresa de excursões de tornados, portanto, íamos a seguir essa mesma empresa e chegamos a uma zona em que estávamos a interceptar a parte norte, ou seja, essa parte norte acaba por ser uma parte caracterizada por muita precipitação, possibilidades de algum granizo forte também e rajadas de vento também fortes.
E à chegada a essa zona de perigo, passaram por nós 2 carrinhas de caçadores de tempestades, que acabaram por voltar para trás. Nós ficámos indecisos entre se continuávamos a seguir para norte ou se fazíamos como os restantes caçadores, de voltar para trás, e por uma questão de prudência decidimos regressar também nós. A nossa decisão acabou por ser o fim do nosso dia de caçada e sem nenhuma outra previsão de outra célula ali próximo, decidimos que o dia acabaria assim desta maneira. Fomos dormir em Wichita Falls, onde se prolongou a atividade elétrica durante a noite.
Dado que estávamos a ter a passagem de uma linha de instabilidade com muita precipitação e atendendo também às inundações existentes nas redondezas, optamos por filmar esta trovada a partir do hotel, de forma a obtermos as imagens a partir de um local abrigado e seco. Aproveitando a pausa meteorológica que se verificava neste dia, deslocámos-nos ao Centro Neurálgico da Meteorologia nos Estados Unidos, o National Weather Center, localizado em Norman, Oklahoma, e onde já tínhamos uma visita guiada agendada. Ficamos assim a conhecer um pouco mais do funcionamento das várias entidades meteorológicas que ali estão instaladas.
So we have about, I think we're up to about 18 faculty, 7 or 8 staff and engineers, and then about 70 students mixed between meteorology and engineering in here. I think a good place to start is over here on the end. Tell what a radar is seeing from an individual target. But one of the things we're studying is what does tornadic debris look like to a radar? Like an individual 2x4 piece of wood or a piece of sheet metal or something like that.
How it looks.
Yeah, exactly, what the return looks like. So what we can do is we can take an object, say a 2x4 piece of a house or even a piece of straw, a piece of hay or grass. We can put it there and we can rotate it in 3 dimensions. And then we can put a radar essentially over there, and all the radar beams that might bounce off the walls get completely absorbed by this material. And all we get is the return exactly from the target that we're looking at. So this is called taking a radar cross-section, an RCS. The whole thing is robotic. It can move back and forth and it can rotate the target for you in what's called the near field. So we actually have been doing damage surveys and collecting some damage that's out in a field that may have happened from a tornado that we can then scan in here and see what it looks like to the radar. So this is called the microfab lab or the microfabrication lab. A lot of what we do is electronics design, right? So we're trying to design one of our big goals is phased array radar, and to do phased array radar you have to do it somehow inexpensively. So the problem is, to do that you need individual transmit receive elements, possibly thousands of them, and we have to do it very inexpensively. Otherwise you'd have essentially thousands of radars in one and be expensive. So what we do is we do a lot of our own design. We design our own chips, our own circuit boards, and eventually if we put it on a system we'll send it out for fabrication on a large scale, but we want to make our own prototypes. So this is basically a prototyping lab. This is our state-of-the-art 3D printer, and I have some examples here. So this is kind of your standard 3D printing, what it would look at like Eiffel Tower. It's very messy, everything. Yeah. This is what this guy can do. Ooh. Much, much nicer.
Very cool.
Obviously an example. So this is a really good example. This is a machine shop. We have a drill press, we have a jigsaw, we have everything we need to actually manufacture metallic parts that we're going to put together in a radar. This one uses 90 degrees of the sector to form the beam, and it commutates the beam around like this. So you're always on broadside. It's always the same because you're moving around a cylinder. So now your polarization purity will always be the same, and because it's a phased array, it's got no moving parts, and it's very, very fast scanning. Each of those columns in the vertical is one transmitter receiver, and I think it's 16 channels, 16 channels, and it's horizontal and vertical, so 32 channels for each of those. And then it uses what's called frequency steering to actually steer in the vertical. So again, no moving parts. So this entire side of this truck in the corner there is all the transmitters and receivers, all the actual hardware. What's cool about this is this operates on only 100 watts of power. So we're talking like a light bulb, 100 watts of power. So a typical weather radar is on the order of 1,000,000 watts of power, or at least a couple 100,000 watts of power. So 100 watts. This is a really good example. This radar can cost 10 or even possibly on the order of 100 times less money than a high power system. So this is something that you can just put this somewhere for relatively little money and get radar where you never had radar before. Is we want really, really fast updates, because a tornado is changing on the order of seconds, right? So you might have a tornado that only lasts 10 seconds, but our typical weather radar might give you a volumetric update every 2, 3, 4, or 5 minutes, right? So we might completely miss a tornado. The idea behind this one is it's a typical dish radar, okay? It's got a dish on the back, it has what we call a pencil beam. So this entire dish back here can go all the way around in 2 seconds, so 180 degrees per second, as fast as possible, using a lot of the spectrum frequency hopping to do this. But it's not fast enough. So this is why we moved to what we call phased arrays. To give you a better idea here, just give me a minute, and I'm gonna make this do something a little bit different. Right now it's stowed so that we can drive on the highway. So this is called the atmospheric imaging radar, or the AIR, AIR. And so instead of sending a pencil beam that goes around and up and around and up and around and up to get the whole volume, what we do is we transmit instantaneously every pulse a wide beam in elevation. So that guy up at the top is called a feed horn, and that feed horn sends a beam that's 20 degrees in the vertical and 1 degree in the horizontal. But then on receive, we use this panel of arrays. There's 36 arrays here, 36 antennas, 36 channels here, and they do what's called digital beam forming. And so they act like a phased array, but only on receive, to look at the different phase shifts of when each piece of the pulse returns to determine what angle it came from. So in a sense, what we can do is we can send out this wide 20-degree beam on transmit, and then when it bounces off the storm and the hydrometeors, the rain and hail, tornado, it comes back, and we use this array to form the beams in the elevation. So we end up getting 21-degree beams every single pulse, and a pulse happens every 314 microseconds. So essentially, 3 times a second, we are getting an entire what we call RHI, range height indicator. There's only 2 radars like this for weather in the world. The other one's in Japan. Toshiba Corporation has built it, and they actually they based some of their design off of what we did. This was built 100% completely by students and staff at the University of Oklahoma. So when we get this close to a tornado, we're getting the highest resolution of any radar ever in history. But we can see the forward flank here, the hook echo wraps around, and then actually into the tornado, we see centrifuging of hydrometeors, rain and hail. There's what we call a weak echo hole. It's taking, all the rain is kind of spiraling into the tornado and then also centrifuging out. So we see this area of weakness here in the center of tornado. In velocity, we see the actual couplet of the main tornado right here. We saw winds, it's early, we haven't processed a lot of data, but on the order of 55 to 65 meters per second at about 250 meters above ground level. So this is looking vertically. So since we're getting that entire vertical structure every single pulse 3 times a second, as we're scanning through, we can actually get this RHI, range height indicator, vertical shot through the tornadoes. And so you can see the high reflectivity, the high power on each side, the low power in the middle. There's higher power down at the bottom where there's debris. And then the velocity structure is interesting. We don't know of anyone who's ever collected RHIs in a tornado with velocity like this. So this is groundbreaking. Actually, you guys are pretty much the first ones to see this data.
But the projectors that are surrounding the sphere, the 4 that we have surrounding here, are projecting a portion of that image onto the sphere surface, and then we stitch those together to make it look like it's moving in unison. And watching this for a little while, you can see that air that was in the Himalayas about 7 to 10 days ago is in the United States today. On the far left, we have products from a national office that we have here in the Weather Center. It's called the Storm Prediction Center. So this is TOTO. It's the Totable Tornado Observatory. So that's how Twister got the idea for the name of Dorothy. It's just following that Wizard of Oz motif. One of the things that we use to get information about what's happening at the surface right at that storm is these mobile mesonet vehicles. And so the instrument racks are put together here in the vehicle bay, and then they're attached to the luggage racks of run-of-the-mill Dodge Caravans. Then they'll take these out and position them accordingly in portions of the storm to get an idea of what's happening at the surface with those. These are also capable of doing balloon launches to get soundings throughout that particular portion of the storm that they're sampling. And so these are spaces right here for helium tanks. And so they can fill up the balloons right out there while they're sampling and launch the balloons in particular parts of the storm. With these experiments, they're trying to figure out the microphysics inside these storms. So looking at the types of precipitation at different levels and looking at the electric field within the cloud too to figure out the potential for lightning strikes where they could happen. There's a camera on the opposite end that will take a picture of the precipitation as it falls through, so they can tell exactly what type of precipitation is in each level of the cloud. So it's illuminated against a black background so they can see exactly what's going through there. And so you can see this one was actually struck by lightning. Some of them get struck by lightning, some of them get hit by grapefruit sail. Yes. This is one of our SMART radars. It stands for Shared Mobile Atmospheric Research and Teaching Radars. These are 13 feet long, and at their tallest they're about 13 feet 4 inches. The standard minimum height for overpasses in the United States is 13 feet 6 inches. We will disassemble and reassemble this radar and take it basically anywhere if we can't drive it to a particular location. So we've taken these to the Gulf Coast and the East Coast to scan hurricanes. We've taken them to Vancouver during the Olympics to scan snowfall in the mountains. This particular radar went out to the Maldives for a tropical rainfall experiment. These are basically the hubs for our project, so where the PIs will sit. And the reason we chose the ambulance platforms, these are again used for our ballooning experiments. And so on an ambulance, you have space for an oxygen tank. But with these, we can take out the oxygen tanks and put in our helium tanks to fill up our balloons out there at the source. So we use these again for our mobile ballooning experiments. We have RF antennas on the top so that we can figure out exactly where those balloons are using GPS tracking. And then we can also communicate with other vehicles that are part of the experiment. So this building was built such that we could combine all of the different weather agencies that were in Norman already, but into one space instead of being in different parts of Norman, in different places. They're all here. We do more than just severe storm research here. A lot of people, when they think of OU and the School of Meteorology, they immediately go to severe weather, but we do a lot more than that here. We have people looking at polar weather, at space weather, tropical systems, lightning, numerical weather prediction, modeling, people looking at Madden-Julian oscillations, MJOs that impact global weather, people looking at El Nino and La Nina, people looking at tornadoes, dust devils on the surface of Mars, and how our atmosphere relates to the atmosphere of Venus. We have people that are here doing that. We have over 1,000 meteorologists here in South Research Campus at OU, about 1% of Norman's population. So these give us measurements of incoming solar radiation. No, believe me, we do. So this is the Storm Prediction Center. It's a national center, so this is the only storm prediction center in the United States. And this is the office where every severe thunderstorm and tornado watch for the continental United States comes from, this office right here. It's about 4 to 6 forecasters working rotating 8-hour shifts. Everybody here in the office has a different responsibility because they have to be covering all of the continental United States at the same time. So the individuals that are sitting in the workstations at the very front of the office here, these are the mesoscale forecasters. And so what they're doing is monitoring storms across the lower 48, seeing if they need to issue a severe thunderstorm or tornado watch. When this office issues a tornado watch, then it becomes the responsibility of the local weather service office to issue the warnings. The individual who's sitting underneath the red digital clock is the lead forecaster. So when the time comes to issue a severe thunderstorm or tornado watch, that individual coordinates with all of the local weather service offices, again, any of those 122 offices in the US, and they will make a coordinated call on that severe thunderstorm or tornado watch for that particular area. We see management officials, we have a broadcast meteorologist, and they're all testing out experimental forecasting tools, products, and techniques. And if these products, if these techniques work in an operational setting, once it's tested here, they can move all that to operations, and it can be something that's used by the Weather Service. And actually here in the United States, we have something really unique in that depending on your GPS location for your cell phone, you will get every single one of those alerts as well. This office essentially covers Oklahoma City, Norman, Lawton, Wichita Falls area in terms of getting severe thunderstorm and tornado warnings and any other local decision. Their general staff is about 2 to 5 forecasters working rotating 8-hour shifts, very similar to the Storm Prediction Center. And they're set up here in the office perfectly for operations. They're all facing one another, and then they can face collectively their situational awareness display in the back. So on those TV screens in the back, they can display different types of information from any one of their workstations. So if somebody sees something interesting on their workstation, they can move that to the back display so that everybody can talk about what's happening. So monitor local TV stations here because they are monitoring severe weather coverage. So whenever there's severe weather in Oklahoma, all the stations basically go wall-to-wall coverage. So they'll cover the storms until they're gone. Each one of those stations has TV crews that go out in vehicles so they can get pictures of the storms from the ground and drive around. Here in Oklahoma, which it's not common to other places in the country, we have helicopters that will hover right up next to the storms too to get pictures of what's going on. They really rely on storm spotter reports too. They take all of those pretty seriously, and so they have something called NWS chat, and so that gives them a way to communicate with different storm spotters, with media teams, with law officials, and so then they can actually talk to them, figure out what's happening with the storm, and then tell people in the public what's going on.